So I'll introduce the next speaker, and for those of you who don't know me, I'll introduce myself. I'm one of the co-organizers of the workshop. My name is Gergana Savova. So our next speaker will be Tim Miller, and Tim will continue the active learning discussion and research, and he will present on how that's relevant to annotating clinical data. So Tim has a PhD in computer science, and he focuses on supervised and widely supervised methods for semantic parsing. And he's working on such tasks as syntactic tree kernels for semantic processing, coreference resolution, and also applying LDA for different classification tasks. So here's Tim.
Okay, thank you. Thanks for having me. And thanks to Burr for a first great talk. That was really excellent and will actually help with some of the introductions of active learning that I'll be talking about. So I'm going to talk about active learning for coreference resolution, and it's going to be sort of a use case I can illustrate, when you start thinking about this as a real annotation problem as opposed to just sort of running active learning simulations. You saw a lot of this in the first talk. Does this actually help? What are the real problems that you run into in your annotation workflow? And we do a lot of annotations on clinical text, and so these are real problems we're thinking about. How do we save annotator time and money? And so hopefully this will, this is sort of a starting point. Can we save time on coreference resolution annotations by using active learning? And so came up with some theoretical things and tried them out based on our knowledge about how annotation really works. So I'm going to start with some background that hopefully most people will be pretty familiar with. So, supervised machine learning, we're all familiar with, requires annotated training data. And this annotation is really expensive, both in annotator time and in some domains, expertise. So in clinical data, we have this problem where you might have data that requires both linguistic knowledge and some medical knowledge. So your choice is, do you take linguists and teach them a little bit about medicine, or you take medical people and teach them a little bit about linguistics? And that's expensive. Coreference resolution in clinical notes is really important for extracting information. You have multiple mentions of a disease or a drug in a note, and you want to know, are these mentions all the same disease, or are they different instances? And so we noticed that there wasn't a lot, at the time that we started this work, not a lot of work on how do you do active learning for coreference. So there's one paper we had found from 2009 on doing active learning for an alpha resolution. And that one actually was mostly a negative results. So we wanted to see if we could find some methods that would be more effective. And so let me just give you a quick background on the task if you're not familiar with it. So we basically want to decide which entity mentions in a document refer to the same real-world entity. And then we sort of group together all the mentions for any given entity, all the mentions that are the same, refer to the same entity. So for example, in a pathology note, you might have, in one sentence, they might use the word cancer, and then in the next sentence, they might use the word tumor, and then they might refer to it as a mass later on. And this is all, in each mention, they're giving maybe a little bit more information about the details of this disorder. And you need to know that a cancer and a tumor are the same thing, and the tumor and the mass are the same thing, and then you can sort of collate all this information in the different mentions together to get a sort of unified picture of what the disease looks like. So the approach that we've used in our system for solving this problem is the discriminative pairwise approach. So the way this works is, you find all the entity mentions of all entities in the note, and then for any two mentions, you train a classifier to say, are these two mentions actually referring to the same entity or not? And then you can take all those outputs of those pairwise decisions and sort of make sure they sort of all are coherent together, and then you can build chains from that output. So in the clinical domain, just to give you a little bit more concrete example, you might have something like, maybe you want to do cohort identification, so you can do pharmacogenomics research. So you might say, I want all the patients with severe rheumatoid arthritis in their wrist joints, say. So this is two pieces of information, And maybe in some notes it's all in one mention, and maybe in some notes it's in two separate mentions. You need to be able to build a model of the pain, or sorry, a model of the rheumatoid arthritis so that you can find this exact piece of information. So the system that we use was from a JME article published earlier this year, and it's a module in CTAKES, which probably most of you are familiar with, the Clinical Text Analysis and Knowledge Extraction System. And as I mentioned, it uses the pairwise discriminative approach. It's trained on the OD corpus, and it uses a lot of the same features as this Ng and Cardy paper, except where they use WordNet features, we try to basically implement them as UMLS features. So, if they're synonyms in WordNet, we basically look for, do they have the same CUI and UMLS? And this is an end-to-end, fully implemented system. This isn't just sort of a, test system. We take, as a first pass, we do the named entity recognition, find the named entities that we're interested in with the system. We don't have gold standard entities. And then we use, use this discriminative pairwise approach to find the mentions in the chains. I will just mention that it's a little bit difficult to compare to some of the general domain systems because it is end-to-end, and because there's this problem of, in clinical data, we have person mentions, which are, sort of ubiquitous throughout the note. You have this repeated mentions to the person. If you do those, you can get an artificially sort of inflated score just by guessing patient for every single mention. And it looks like the task is easy, when in fact, it's pretty hard on all other kind of mentions. And the last thing I'll mention is that the work we did is component level, so not system level. There's different types. There's pronouns, and then there's named entities, and then there's other sorts of this and that sort of thing. We looked at the component that just tries to match up named entities. So this is a binary classifier that its input is two named entity, a pair of named entity mentions. And then we use a discriminative classifier, SVM, trained on all those. So now, this probably isn't necessary after the previous talk, but I'll just walk you through maybe so you have the terminology so that when I extend the algorithm later, you'll see what the analogies are. So sometimes the sort of normal way of doing supervised learning is called passive learning, where you would randomly select examples to have annotators label. But active learning, in contrast, starts with a, let's see. Start with a seed set S, which is some subset of your whole data set D. And then you get the oracle labels from your annotators usually. And then you'll train some model M. And then you'll keep iterating where you select a single example based on that from your current data set based on your current model. And then you'll get the label for that, add it to your seed corpus, retrain, and then repeat the loop. And then you can stop according to some stopping criteria. And so just to sort of zoom in on this a little bit, the train function is classifier specific. This is something that may make a difference in what you do during annotation time versus what you might want to experiment with after you have your annotated data. So in our case, we use a SVM, but you could use a decision tree or whatever. This select best example is where you sort of fit in the different selection paradigms from active learning. So one of the most common ones is uncertainty sampling, where you can use the sort of simplest way to think about it, or the practical way to think about it, is you have a decision boundary in your classifier. You just take the example that's closest to this decision boundary, and that's the one that the classifier is struggling with. You get the label for that one, and now you have a label for a difficult example. And you can see this, the active learning paper by Bersettles for a lot of other techniques. Okay, and so another thing is I've sort of described this select best example as giving you a single example, but it's possible, maybe you want to save time and just or if you have a slow classifier training procedure, maybe you want to get 50 at a time, and so you're not constantly having the annotators wait for more. So you could try and get a sort of batch selection where you get 50 instances instead of one. Sort of our in-house active learning expert, Dima, told us that usually doesn't work as well. So we did one at a time, and then we could actually, in our experiments, we're doing simulations, so it's reasonable to retrain after every one. And so typically during research, active learning research, you do simulations. And so all of this D is actually labeled. So this oracle is not really an annotator. You're just sort of uncovering the label and looking at it. In real life, if you have real annotators, the oracle is a human, obviously. So the issue that we had that led to this work is that the way that we've described it right now is probably not really suitable for the way that coreference resolution works. And there's some really practical issues about the way that the annotators have to think when they're annotating examples. And the idea is annotating coreference requires some level of contextual understanding. So if you think of a problem like word sense disambiguation, you can just give the annotator the sentence and the word, and that's usually enough context. They don't need to read the whole document to understand. Coreference, on the other hand, you may have example pairs that are, 4 paragraphs apart. They may be multiple sentences apart. And if you see the word cancer at the top and the word tumor at the bottom, you need to know sort of what was the flow of the document, what was the sort of discourse in the document that led this mention and this mention. Are they actually the same, or is this a new mention? So because the pairs can be very far apart, you need to have the annotators need to understand the context and the discourse in the document. And there's sort of a lot of overhead. So if you give an annotator one pair in a document and they happen to be very far apart, and it's likely that that's actually a difficult example. So that's a likely example that they would see. Now they have to read this whole document just to label a single instance. So we think that this is, because of this reason, that the traditional way of describing or doing active learning like I just described probably isn't super practical. And so this led to the idea, is there a way that we can take advantage of this time spent learning the context without wasting annotator time on useless examples? So they get the context and maybe label all the examples that are actually difficult and ignore the ones that we don't need because they're useless, and maybe they'd save some time there. So now I'm going to talk about some of the methods we use to explore this idea. So instance selection is the baseline or default way of doing it, as I just described. And so here you would generate all candidate pairs from a given document, and then you would pick the one that was the most difficult for the classifier. So as I just mentioned, this is impractical. It also can be slow because you have to retrain the model after every instance is selected and labeled. It does have the advantage of being very straightforward. At least with a binary classifier, you can just take the one that's closest to the hyperplane. And there's a lot of work using this sort of framework, and in simulation at least, showing that it produces better results than passive learning. So we think we should probably be able to get this to work. This previous negative result that I reported used batch selection. Although I should mention, there was a paper this year at NACL that showed that they got a negative result doing this sort of thing, which we thought, well, I'll just foreshadow, we actually got a positive result. So not sure how to reconcile that exactly. But the point of doing any experiments or develop any methods in this really impractical method is to say, well, if we want to build on these instance selection methods for doing batch selection methods, then we need to actually make sure that this works in the first place. So then the next idea we had was, okay, well, instead of doing instance selection, let's do document level selection and see what happens. So now instead of saying take 2,000 instances and only label the 1,000 best ones, now we're going to say take 50 documents and only label the 25 best documents. Now this fits, pretty much perfectly into our existing annotation workflow. That's the huge benefit of it, because they're already annotating whole documents. If we can get this to work, we can find documents that are, sort of uniformly better than other documents. That's perfect, right? That's exactly what we would. We wouldn't have to change our annotation workflow at all in terms of, how the annotators think about annotating coreference. And it probably wouldn't be as slow either, because then you only need to retrain the model after a document as opposed to after every single instance. Now, it's not quite as straightforward because there aren't any sort of standard document level metrics for how good a document is. So we basically had to invent some methods that would take the instance level and build up a document level metric that took into combination all the instances in that document. And so we came up with, it's sort of easy to brainstorm these document level ones based on the instances, and we came up with a bunch of them. So I'll just go through the list. We started with, why don't we just take the find the best example, the sort of normal way we would do it, and just label that whole document. Then at least we'll get one really awesome example. Another way is take the average uncertainty for all the examples in a document and just take the document with on average, the most uncertainty. Another one is, instead of looking at uncertainty, look at, does the classifier think this document has a lot of positive examples? Because the coreference domain often has very skewed data sets, we thought, well, maybe the documents with a lot of positive labels will be better than the ones with negative labels. And then going back to uncertainty, we said, well, let's look at the best example from the most uncertain example in the document and the worst example, the least uncertain one. And let's just take the document where the difference between those two is minimized. So in other words, maybe we won't have very many really bad examples, even if we don't have the best one. Then we said, well, okay, let's take the worst example and take the document where the worst example is not that bad. Then we're not getting any really bad examples. Then we said, well, let's put a band around the hyperplane that separates the two classes, and then take the document with a lot of examples inside of that band. So between, if you're thinking in terms of probabilities, between 0.4 and 0.6, take the document with the most number of examples within that range. And then we said, well, let's just take the document, try taking the document with a lot of positive examples, regardless of what the ratio is. Okay, so, and I'll foreshadow a little bit here, because I'm going to go to the next method. And the reason there's another method is because these methods didn't really work all that well. So the next thing we tried was sort of a hybrid approach between the two, and we call this one document inertial selection, or you can think of it as sort of sticky instance selection. And the idea here is we find the best example using the sort of normal methods, the instance selection methods, and then to choose the next instance, instead of looking through the whole corpus, we just look in the document that we were already in. And the idea here is, if a person the annotator has to read that first example, they get all the context in their head, they're sort of thinking about this document already, instead of sending them across the corpus to another document altogether, let's just find the next best example in this document. It's still probably pretty good, and then they already have the context in their head, hopefully. There's less overhead in sort of reading this document. And then at a certain point, maybe we'll run out of good examples in this document and we can send them to another one. So the metric is, again, pretty straightforward. We can just use regular instance selection. That's nice. It maybe has the same slowness as the original one. Practical, well, I think in theory we've attacked this one problem. So it's, you would think that it's more practical. It's an empirical question whether it's actually more practical. But hopefully we're sort of attacking this one problem. And so just to put this in sort of algorithmic form, it starts out very similar, where you get a subset that you train and get a model. You select the best example from this document, D. You select the best example from the corpus, your data set D, and then you get the document that that data instance belongs to. Then you get the label, retrain, and then you select the best example. Where here, select best example is scoped only over that document, right? And then if that instance we selected D meets some criteria, then we keep going inside this document. Otherwise, we go to the outer loop and start and select the best example from the corpus and move to another document. So hope that was clear. So now I'll get into the experimental results of these different methods. Excuse me. So we took the from the OD corpus, we used the notes from the Mayo Clinic section, and there's also some notes from the Pitt section, but we found that they were actually fairly different. So we just wanted to focus on, not worry about domain adaptation, just focus on the set of the corpus that was the same. We generated the candidate coreference pairs using CTAKEs, and then we tested both active learning and the passive learning classifiers on held out data after every single retraining. And then we generate the active learning curves, which you were introduced to in the previous talk. So I'll just go ahead. And our first sort of baseline result looked great, right? We're finding that around 500 or 1,000 instances, we're reaching the same performance that we get at the end with active learning. So this blue line is the random baseline passive learning, and the red line is our instance selection. Remember, this is the impractical but it's the building block for our other methods. So that's good. If we didn't have a curve, reasonably good-looking curve, then we probably couldn't even proceed past here. So this is the first document selection level experiment. So you'd be hard-pressed to tell which one was random if I didn't have a key up here. But the dark blue is the passive baseline, right? And they're all sort of around that same line. It doesn't look like basically we're getting any benefit from these methods. Yeah, I don't know. Then it gets worse when you look at the other method. So I didn't put them all on one slide because there's so many of them, but these are the first 4, and these are the 3 that are actually a little bit worse. So somehow you're doing worse than random. So then this led to our instance selection, and here we get a really good looking result again. So the blue again is random, the green dotted line is the line from the first one, and the red is when you do inertial document sampling or the sticky instance sampling. And so here we're back to getting almost the same performance, or pretty similar performance that we get with regular instance selection. So it looks like you don't lose much in the way of accuracy or time by sticking within the same document instead of skipping around documents. So that's really nice. So a little bit of discussion. Pairwise works great. That's very good to see. The document-wise result, given some of the previous literature that shows that it can be difficult to do batch selection, it maybe shouldn't be that surprising. It's very difficult to do, and with document selection, you're actually handicapping yourself a little bit more because you're not even taking 50 best examples. You're taking sort of 50 random examples with 1 or 2 of them being really good. So from hindsight, maybe it's not that surprising that it doesn't work. And so the document inertial method works pretty well. So the question is there a real improvement in practicality? And this has something to do with the empirical sort of distribution of context. If you get one example where you had to read a lot of context, does that actually help you read the second example? Is it the same context? Is there overlap? Or are you going to be skipping around a big document? So that's the point where actually doing this on real annotations would be great. And there's another practicality question, which is it useful to have partially annotated documents for coreference, where you just do the difficult pairs? What sort of paradigms is that useful? Are there other sort of machine learning paradigms where it doesn't matter if you have really good examples, you need all the examples in a document? Another practicality issue. And so future directions, I'm not sure number 1 is a high priority, but they're easy to think of, so they're easy to run experiments. You could try doing more document level selection. I'm a little skeptical that the document level will work. It might be interesting to show sort of building a model of what's going on in that document level selection and sort of try to show whether that model is true and show that it really can't work. We'd like to do practical experiments with our annotators showing, does document inertial actually fit into a workflow? Does it improve annotation time? Or are they just going to be doing all the hard examples and taking the same amount of time? And then we sort of like to look at, can we build methods for a corpus of partially annotated documents? And so that concludes my talk. I'd like to acknowledge all my colleagues, the reviewers of this work from the original paper, and the funding sources. And then, sorry, this is a slightly older version that has the old download link. If you want to download CTAKES, it's on the Apache Software Foundation. You can just Google Apache CTAKES. All right, and if there are any questions, I don't know how much time I have.
We have time for 1 to 2 questions.
So you were working from pairs. I wonder if you've looked at trying to work from individual, like one side of the pair. So rather than asking them for a random pair, you figure out which of the entities you're most uncertain about the relations around, and then ask them to annotate the entire chain for that entity. Does that make sense?
Yeah, no, yeah, we had some sort of preliminary discussions around that, and I think that that is true that certain chains actually are difficult rather maybe than just pairs. I think the difficulty is once then you do that, then you're throwing away, you might be losing a possibility that you could just read a section of a document instead of reading a whole document, right? But
So my question is related to the fact that you've only done simulation studies so far, so you've got number of instances on your x-axis. And I know that when Burr Settles gave his talk earlier this morning, he said it looked great when we had instances on the x-axis, and when we took real annotator time, not so much. So do you have an intuition as to hopefully why instances in this case would be I mean, if every instance takes the same amount of time to annotate, you're golden, but if some instances take a lot longer to annotate than others, you could have the same issues. Do you have an intuition about that?
I mean, I guess I don't. I think the only way is to check. I mean, the intuition is that, of course, there are different amounts of times, and then the empirical question is just like, is it so bad that it doesn't make it worth doing active learning? Yeah.
So this isn't a question so much as a comment. So most of these active learning evaluations look like they're geared toward overall 0-1 evaluation of a corpus. That is, you care about annotating every item. We've done a lot of work in practical applications for customers at our company where the goal really wasn't to annotate every item, it was to go fishing. So you wanted to do something like you had a very large set of data and you wanted to find instances in which you were very confident. For that, what you can do with active learning is change the threshold at which you look. So instead of looking at things that are close to the decision boundary, 0-1, look to things that are close to the decision boundary you're going to make. So if you're trying to make a high precision system, you'll typically up the threshold in something like an SVM setting, right? So depending on the task, right, the version of these things you want is very different. And what happens around the margins very often, especially in these kinds of simulated tasks, is there's a lot of noise in these corpora. You know, people call them gold standards, but there's lots of errors in them. So what you're going to find is that your system's very uncertain about examples that are around the margin. Right? So, sorry, that wasn't really a question so much as a comment.
No, I mean that's certainly true. That this is one of the sort of one of the other dirty secrets of active learning, I think, is that the margin is not always, or the sort of decision boundary is not always the uncertain examples. It's oftentimes the noisy examples too.